Today we have Alaa Eddin Alchalabi as our speaker. Alaa is currently pursuing his PhD in electrical and computer engineering from the University of Ottawa, and he holds the prestigious Ontario Trillium Award. He's also working in Swamio Media as a research scientist, and his research is focused on applying AI to multimedia systems, and he has been involved in several international projects. So he has a very impressive background, and he'll be presenting today on fair server selection in edge computing with Q-Value-Normalized actions suppressed quadruple Q-Learning. So with this, the floor is yours, Ala.
Well, thank you so much, Niraj and Sabina, for the invitation to present my work. And I want to take a moment and thank everyone for taking the time to be here in this lovely seminar. And I'm going to start by sharing my screen, and I should be able to do that in a second. Can you see my screen?
Yep.
Okay, let me make it bigger. Well, yeah, thank you again for the introduction. My name is Alaa Eddin Alchalabi. I'm a PhD student at the University of Ottawa. And today I'm going to be talking about my thesis and my PhD that I'm going to be hopefully defending in a couple of weeks, maybe like in a month or two. And yeah, and this project was mainly in collaboration with Discover Lab at the University of Ottawa and also Swamio Media, which is a startup in Eastern Toronto that deals mainly with esports, the esports industry in general. So the title of this presentation is Towards Fair Server Selection in Edge Cloud Networks, a Reinforcement Learning Approach. So it's mainly, we're trying to apply an AI on a prospective edge cloud network that would deal with mainly games or any real-time application. We also divided this into two different components, and that's going to be DS Quad, which is like a delay-sensitive server selection system, and also one part of it is Q network, and I'm going to explain these parts in detail. So for the outline of this presentation, I'm going to divide the presentation to 4 different stages. Like one of them, I'm going to start with the introduction and laying the ground on some background on the motivation and the problem. Then I'm going to talk about how do we define this problem with a few of the system terminology and some formulation. Then I'm going to talk about the solution, which is Q-network, targeting that specific problem, and then I'll finish up with a conclusion with a roadmap and some outcomes of this project. Feel free to stop me at any time. I think I can see the chat or probably raise your hand. I'd love to answer your questions. And also I'll be stopping in between these sections in order to put some more time to for any kind of clarifications. So starting up with the background and motivation behind this work. So what we're interested in is building an AI-enabled edge cloud solution that's going to accelerate the performance of real-time systems. What you can see here from the left-hand side, when, for example, an example of real-time systems is online games or cloud games. They require a few people from around the world, for example, like a player from India, another player from Dubai, and someone in France. They wanted to play a game all together. They have to connect to a central server in order to play that game. Or let's forget gaming for a second. Probably like any transaction or any application that needs a real-time performance would have to be centralized in terms of computing. What we're trying to build is more of a decentralized approach, where instead of connecting to a central server, these players can somehow connect to the edge server closer to their proximity, and then using like edge computing with the advanced 5G networks that will be able to host this operation closer to the user and therefore leveraging higher bandwidth and also lower delay measurements in terms of these applications. And one candidate of doing this is using deep reinforcement learning approaches, because in terms of selection, we have a problem with selection, we have a problem with estimation of delay, because you'll have a big, very huge network. So you won't be able to estimate delay and bandwidth. And also the selection had to be very, very smart. So deep reinforcement learning approaches would be very ideal in this situation. So a bit of background on gaming. So the gaming industry is huge. It's above $200 billion in gaming market cap. That's, I think that was in 2019, 1.7 billion only in esports, more than 3 billion gamers and 500 esports viewers in various platforms such as, and I think one of the most viewed games was Dota, I think last year, that surpassed 300 million viewers at once. What you can see on the site is Swarmu's application that connects and allows people to participate in their games tournaments that they have, and then they also manage to organize. So why do we choose edge cloud gaming? In this sense, I mean, taking an advantage the gaming industry, we can bring the network and also the computation way closer to the user, and also like with the advent 5G and edge computing that would require a lot of data handling to be done on the edge side, which is very close to the user. That would reduce the latency and boost actually the performance. And one candidate that has the power of doing this is telecom operators, because they own a lot of computing power that most of the time it's idle, and it's not actually operating with half the potential it could. So the operators have the network infrastructure, and they can come up with the architectures to cope with any of these problems. I think Google, Amazon, and Microsoft, they entered the game of edge computing. They started their own projects, and also they're partnering up with a lot of telecom operators across the world in order to start monetizing from this movement. So this would enable telcos to monetize, and also would also connect with millennials and digital natives who will be very tech savvy and very thirsty for a higher bandwidth and also low latency in terms of applications or in terms of games in general. So an example to that would be like telcos offering compete offers, and also packages specific for gaming and specific for like higher performance in order to charge more and then probably gain. So it's a win-win situation for telcos, game providers, gamers, and everyone in this game. Then very tiny background in deep reinforcement learning. The advantages of deep reinforcement learning is there's a huge family of algorithms that are online. They can be ongoing, which fits the nature of networks. Of course, some of them or most of them are model-free. That will help the sustainability and the scalability of these problems. And of course, since we're dealing with networks, and since we're dealing with the computer network, that the architecture and the structure changes because it's not supervised from like a central approach. These algorithms will be able to learn on the go, and then also like modify the parameters based on what data is actually received in real time. It's also hard to predict the state of networks because of the average delay and the traffic that depends on like the day of week, the time of day, and various factors. So these algorithms will be able to learn the time, for example, associate the time with the delay and the performance of the network, learn the traffic, create embeddings for these features. Also, like it will help with user ratings, estimating delay, and also unexpected conditions, and try to identify them before they happen. Let me give you an example on this in the map here. So let's say if you are in this node here, and you want to connect, for example, to one of these nodes, instead of connecting to Greenpeace Canada let's say it's closer than John Bennett, so the algorithm, for example, should know that this is a very easy node, and the computation is going to be very expensive. And not only that, but also in the future, if this choice was taken, this would somehow create more traffic, because this is like a central node, or this is like a bottleneck on the network. So the statement I put here is that the optimal choice in the current time is not always the best choice for the network. So because there are so many interdependencies, such as traffic, and also you have to take the whole picture in consideration while making a decision, or while taking a decision to connect a dot or like a node to a network to another. That done. Yeah. I mean, that was a very short introduction, but if there's any question, I'll be happy to take them.
When you were defining optimal, to say optimal is not best seems like an oxymoron. Can you maybe, obviously, you're saying that the simple approach is not appropriate. You have to think about long-term effects and so forth.
True, yeah. When we define optimality, it's just like what is the theoretical best solution for the current setting. Because most of the current algorithms will be taking the optimization approach, where the optimization, I mean, they always assume optimality when it comes to that. And then, for example, if you want to connect users to servers, and then when you optimize the network on that, the optimization will give you the optimal choice in the current setting.
Well, yeah, I'm saying the definition of optimality, the thing you're evaluating, is the wrong thing, right?
True. Yeah, exactly. Well, yeah, network people have to change their definitions, I guess.
Thank you.
Yeah, no problem. Any other questions? Great. So now we'll be jumping on the problem definition and defining some system terminologies and formulations. So this is today's map. Let's assume that the users are going to be in distributed, across the world, and the number of users is going to be way larger than any other computing devices that we have. Let's imagine that this icon here, the edge nodes, are distributed in less density and then less number of users. And then few of these edge nodes are going to be selected to be delegated edge nodes. And I think in the next slide, I'm going to be explaining what these terms mean. Just for the whole picture, you'll see that users going to be the number of users is going to be way more than the edge nodes, and then few of these edge nodes will be selected to be delegated edge nodes for computing and for creating some centrality in the architecture. So edge nodes are mainly user servers. They can be user servers. They can be either like rented servers, and they can be also actual edge nodes at base stations that could host these tournaments and host these games, or host these any of the time latency sensitive applications, in order to cover areas that are not covered by a strong internet connection. This type of user on this type of node will be ranked by certain ranking criterion in order to be evaluated in later stages. The delegated edge nodes will be a special edge node that will be selected as an entry point for nodes that will join the network. And then we'll also handle these sessions, or assignation of the sessions in different regions, and will perform monitoring tasks, as well as like some recovery in terms of failure. And also most of the algorithm will be running on these edge nodes, delegated edge nodes. In order to formulate the problem defining the optimal approach, we came up with a few ranking mechanisms, or like formulations, and these ranking methodologies. One of them is the bandwidth to delay ratio, which tells us how good is the edge node connection to the network session. The second one will be like user feedback, how good was the experience during the network session, and that's going to return the quality of experience. We can also rank these edge nodes based on the capabilities. For example, we can set the first level to have a few a few gigabits of RAM, and then what kind of GPU does it have, and then based on that criteria, we can put them in different ranks. And then lastly, like a weighted rank for all of these four, and that's simply like simple weight that will be multiplied by the separate three. The map on the right here that shows an actual user to edge node assignation, where, for example, we have this number of users that were already assigned to this edge node, and then these few users that will be designing to either join this or edge this edge. And these two edge nodes will be connecting to a dedicated edge node. Well, in order to define the perfect allocation between users and servers, we'll be taking the consideration of the ranking. We'll define some kind of a network metric where we'll have the usable bandwidth between the user and the edge, and divided by the actual delay between them. And then using the optimization approach, we have to maximize the network metric between each user and server, and also the ranking of that server. So there are many cons for these approaches. It's static, of course, because if a user joins or leaves, or probably if we want to add a server, that has to be recalculated and rerun again. And then also, like, if you want to introduce new constraints, probably if it was a game, also that would require to revisit the formulation and then reinvest more time in terms of optimizing this approach. That was very short, but if there's any questions regarding this, I'll be happy to stop and answer them. No? Okay. Then I'll be talking about Q-network, which is our the actual work, or the actual piece of this work that will deal with fair server selection in edge cloud networks. Okay, so it's the Q-network utilizes reinforcement learning to fairly match servers and users. And then I'm going to define what do I mean by fair matching. The notion of fairness is to reduce the variance of the delays of the selected pair. So as you can see from this slide here, or from this figure, this is like an actual data that we have collected from, I think, 151 users and 151 edge nodes, where we simulated connecting each user to an edge, and then using a closest match approach. And as you can see here, there's the very first users will be selected to the very best servers that exist in the network, but the very, I think, the last 20%, 25% will suffer from using whatever available users are there. And we would like to eliminate this effect by somehow like matching things closer to the average, closer to the global average, and then reduce that variance in the selected pair. So what we have built in Q-network is that we have to somehow input the IPs and the locations of edge servers and users. We somehow would use either an estimator, I'm going to talk about this right after Q-network, or an actual delay measurement, then pass it to Q-network, and Q-network using the RL would come up with an edge to user assignment. Jumping inside Q-network, so what it uses like a modified Q-learning algorithm to perform this fair matching. It's modified and it comes to 3 separate stages. So we introduce something we call action suppression, which reduces the practical difficulties in using RL and large action spaces, and reduces the taking some actions that are nearly occupied. We also used quadruple Q-learning, which is using 4 different Q-learning models in order to come up with an ensemble model that outperformed the actual 4. And then we use also local normalization in order to fairly compare the 4 different models all together in one. So so instead of 1, we use 4 different models, and then we ensemble them using local normalization and introduced local action suppression. So the contributions mainly is to consider the standard deviation of the latency while you're assigning, and the change and the rate of change in the standard deviation of assigning an actual user to an actual server. This will make the algorithm solving a multivariate, multi-constraint problem that would fairly assign edge to edge servers to users. I think I'm gonna jump slightly in detail in that. So this is like what traditional Q-learning is. We have our a beautiful update and also like this kind of set of rewards with the maximum Q values from previous states. What we have introduced is that we introduced availability of these actions, and also somehow we came up with a way to suppress the actions before they actually are not available. And then once they are not available, we eliminate them from the approach, from the actual list of available actions. Then the second one was introducing the quadruple Q-learning, where we have these 4 different models working with each other. So we introduce like a total distance, which is it's gonna happen as a it's going to act like a global variable where we have distance functions that will calculate, will help us calculate the next rewards. And then after that, we normalize the values in order to use them in an ensembled way. So jumping in detail more in the 4 different models. So the very first model we used had the negative reward of the distance function. And in this model, that would aim to reduce the distance between any selected pairs. And you'll be able to see from the results that somehow it spreads the spectrum on edge to user assignments. And you'll see that every time the action was taken, it reduces the distance as much as possible. But for the second model, we used the standard deviation, the negative value of the standard deviation, of the current standard deviation of the assigned pair. That would have an effect, of course, on reducing the total standard deviation of the delays, but also when you think about it sequentially, so every time you assign a pair, you take that standard deviation and just assign it as a reward, and then the standard deviation will, of course, somehow be learned, throughout the learning process and throughout the episodes, and then the very final outcome will have the least amount of standard deviation in terms of delays. We came up with 2 different models, and this is mainly what had a huge effect on the results, is that we use the change in the standard deviation. So this is not only reduces the standard deviation, but also reduces the variations in standard deviations. So now we don't only want a small standard deviation, but also we want to reduce that big change in standard deviations. So we used one without an absolute value and one with the absolute value. You can think of this process as we use the distance as a distance function. This could be a delay, and this could be any other distance function. Geodistance was one of the things we have used. And then the standard deviation of delay, which is the variance of the delay, or the change, or the derivative of the delay, if I might call it. And then the change in the standard deviation, which can be called, or can be imagined as the second derivative of distance. And then these 3 models, or the 4 models, will be ensembled all together using local response normalization, and then then the maximum action will be taken. Some results of our work is currently shown. So the map on the left shows the distribution of these users in dots, and then the servers will be in axis in North America. This was the very first model, which has matching closest servers to closest users. The ensemble model, which is the last model, that would show that the assignation somehow was closer to the average, and you'll see that the numbers were shifted up a little bit for the very first users, but also shifted somehow like down for the very last users. So you'll see, of course, that if that was trained for a very longer time, that you'll see like something closer to a solid line here. If you have, for example, infinite number of users and infinite numbers of servers. We've also like tried other functions such as like some convolution functions, and I think I'm going to explain that next. But it's good to be mentioned that the lowest standard deviation, which is the fairest in our notion, was the one that has the quadruple Q-learning, the four models altogether with local response normalization, while the other models perform pretty well compared to the closest matching. So we use the very closest matching and then the second closest. So every user was matched to the second closer server, and then we used the 75th percentile closest because they were 150. So we used, sorry, the 50th percentile in terms of matching. So we somehow like rank them and then assign each user to the 50th percentile of the delay in terms of delay, and that produced slightly better results than just using the closest. But of course the best result was for the ensemble model. I think now it's just more results and probably visualizing these results. This was the first anchor, which is using the closest matching, and the second one was using the second closest, which is almost the same as the closest, but it has a slightly less standard deviation. The third one was the 70 percentile, which you can see somehow like the introduction of fairness was somehow like obvious in the very first steps because this was matched to the somehow the closest, or like somehow the 50% closest server that it could find from the list. These are the results for the models that we have presented. So the very first one was the having the result as a reward, has a distance as a reward, and you'll see that the spectrum was spread in the vertical axis, where each user was somehow the distance between the users were somehow preserved. Then when we introduced the standard deviation in total was somehow reduced, but that did not create the fairness that we wanted. So that's why we moved to model 3 and 4, where we introduced the variation, or like the change in the standard deviation, and that produced somehow, it started to form that somehow line to introduce the notion of fairness. Then model 5, which have the quadruple Q-learning, the four models are ensembled, and then the same model with local response normalization, which brought these the numbers down, and also it has the best results when it comes to standard deviation. It should be mentioned that the average here was also preserved, and the conditions of the game was also consistent. I think the condition was around 50 to 75 milliseconds, so the matching did not happen if that was above the threshold. We also compared it against conventional algorithms and heuristics. So the very first one was calculating an average from a very first node. So we just take a random node, and then we create the best delay and the worst delay in terms of the spectrum, and then we calculate the average based on the very first node. This of course, its variance, it's different on the very first node that we choose and the spectrum of the servers, but it was noticeable that yes, the notion was there, but it highly depends on where the choice of the very first network was, and the best model was model 6 that produces actually much better results when it comes to that. These models were good in terms of standard deviation, but they produced very high averages compared to any other models. This was like talking about Q networks. So I'm going to stop here for a second and get any questions that you have regarding the Q network allocation. No questions? Okay. in terms of delay measurements, as I mentioned in previous slide, in order to come up with these models, we had to either come up with a way to measure the delay, or just measure it like in normal pings, or there was some estimating algorithms in the literature that we could also use. So we came up with this approach where we could estimate any delay between any two nodes in the network using deep learning. So this was a work that was a collaboration between two students in Discover Lab, Shadi and some other friend, I think Sadi. And then of course, they used deep learning algorithms to estimate the latency based on a very big data set that was called a King data set. It was, I believe, it had 1,300 nodes mesh. So it was 1,300 by 1,300 nodes. And then I think it was collected in 2002. So they came up with this model that has a feature selector where any IP address of this mesh was entered to a feature selector that would have a source region, a destination region, the ASNs, which is the service providers, the coordinates. So it uses also the geodistance or the geolocation, and then from the regions we came up with the word embeddings, and then the geodistance was calculated. This was normalized and then fed into an AI model in order to estimate the delay. It should be mentioned that we had a delay that was we had the labels ready, so that was very easy to train. In specific, the AI model uses a multimodal deep learning network, which was a combination between two different neural networks that is based on CNNs. So it just slices down the data into local and remote, and then feeds into each of these models into separate ones. So it was pretty simple. We had only two different convolution layers, a max pooling layer, a flooding layer, and then a fully connected layer in order to come up with this output, which is the predicted latency. This is an example of how the multimodal model looks like. So the dataset was again divided into a local dataset and a conventional dataset, and then there was somehow a local output and then another output that would be fed later into another one that would be concatenated in order to come up with the multimodal output. So the two different CNN models were somehow frozen after they were trained, and then the output was concatenated in order to create that multimodal approach. The performance of team, of course, I think was exceeded any other model in the literature, such as using like simple tenants. Phoenix was one of the delay measurement estimators that uses, if I'm not mistaken, using like the spring theory. And also there was Vivaldi that uses like multiple pings in different locations and uses somehow like a clustering approach. There's IDES and DMF as well. So these were all evaluated on the King dataset, and then Dean came up with around 96% of accuracy. I think that's it for the technical part. I'm just going to jump to the conclusion if there's no questions. Okay. So in terms of the roadmap and the outputs of this and outcomes of this work, so we illustrated an approach for service selection to ensure that the latency constraints are preserved and also is applicable for different application constraints. Of course, that is dependent on the advent of 5G, which we are relying on the upcoming edge cloud infrastructure and also the access to these edges. Also, like we attempted fairness, which is to reduce the variance and the delay, and also reduce that variance of delay between players in a single session and also globally. So in terms of roadmap, of course, we used online and offline training. Then we have trained it on like the King data set. Later, we were thinking of using DQNs and contrastive learning in order to create embeddings to understand networks and represent networks in a more compressed way. Then probably we would somehow starting to revisit the optimization and then compare it. Then the very last step is integrating that into INF5 network slicing, because after estimating the delay, selecting the fair location for the session, securing a network slice would be an ideal continuation of this project. So this project has produced a few publications. Received the first award in the category of technology and digital transformation in the graduate poster competition in the University of Ottawa in March 2019. And also we have signed a patent that was accepted, I think 2 weeks ago. There was two journals, a conference, a few posters, and also a technology transfer in order to be deployed and applied in Qvalue's network. So it was licensed, and then I think it was implemented around beginning of this month. That's it. Thank you all for being here, and I'll be happy to answer any questions if you have. Any questions? No? Okay, so I think I'm gonna hand the mic to Niraj and Sabina to continue the session and conclude.
I'll just pop Alaa's email in the chat window. Let me just pull it up in case anybody thinks of any questions after, or you can just reach out. So just give me 2 seconds to pull it up. Okay, I put it in the chat window there for anyone who needs it. If nobody has any questions right now, I will stop the recording and say thank you very much for coming and doing presentation for us.
Yeah. I think I'm gonna stop sharing the screen.